We now discuss the solution of a problem from the section Permutations and Combinations. And the problem is based on the fundamental principles of counting. And this question has appeared in the joint entrance examination main held on 24th June 2022 in the second shift. The problem is the number of 7-digit numbers which are multiples of 11 and are formed using all digits 1, 2, 3, 4, 5, 7 and 9 is. So we have to count the number of 7-digit numbers which are multiples of 11 which are formed using these digits 1, 2, 3, 4, 5, 7 and 9 with no repetitions. We now discuss the solution of the problem in detail. Given the digits to be used to form the 7-digit numbers are 1, 2, 3, 4, 5, 7 and 9 with no repetition, note down that the number 6 is not there in these 7 digits. Agreed. A positive integer, capital X, is a multiple of 11, means 11 divides X. And we have the divisibility rule for 11 that says the difference of the sum of the digits at even places of X and the sum of the digits at odd places of X is a multiple of 11. That is the divisibility rule for 11. Let capital X be a 7-digit number of the form A, B, C, D, E, F, G. A, C, E, G are, are the digits at the odd places of X. B, D, F are the digits at even places of X. Agreed. Where A, B, C, D, E, F, G belongs to the set consisting of 1, 2, 3, 4, 5, 7, 9. X is a multiple of 11 implies the sum of the digits of X at odd places is A plus C plus E plus G minus the sum of the digits at even places of X, B plus D plus F, the difference, the sum of the difference. This is the sum of the digits of odd places and minus the sum of the digits at even places is a multiple of 11, 11k, where k is a integer, k belongs to Z. And the sum of all the digits a plus b plus c plus d plus e plus f plus g is 31. So these are the two equations to be satisfied. So from this it follows, it's not that easy, but it follows either a plus c plus e plus g is 21 and b plus d plus f is equal to 10, the sum is 31, or a plus c plus e plus g is 10 and b plus d plus f is 21. This is the conclusion that we are drawing from the above two equations. And if you are able to draw these conclusions, it's okay. But otherwise, I'll show you a method of doing it. Now, let SE be the sum of the digits at even places of X and SO be the sum of the digits at odd places of x. Then SO plus SE is 31. This is the equation. SO plus SE is 31 and SO minus SE is 11k. So this is the one. So this is the one. So from these two you have to get these either or conditions. Now therefore if you add them, 2 times of S naught is equal to 31 plus 11k, and if you subtract, then you will get a 2 times of SE is equal to 31 minus 11k. Agreed. Suppose you say k is equal to 0. If k is equal to 0, then SO minus SE is 0. That means SO is equal to SE. Then 31 is equal to SO plus SE, and SO is equal to SE. Therefore, this will be 2 times of SO. And 2 times of SO is even, 31 is odd. This is not possible. Therefore, k is equal to 0 will not arise. Therefore, S naught not equal to SE and k not equal to 0. When S naught not equal to SE, then we have two possibilities. The first one is either SO is greater than SE or SE is greater than SO. And from these two, the following can be proved. So what is that? If SO is greater than SE, then k is equal to 1 is only the solution. And if SE is greater than SO, then k is equal to minus 1 is the only solution. When k is equal to 1, then this is the either case. When k is equal to minus 1, this is the or case. So that is the conclusion that you can draw. So this is how you can draw these two conclusions. Now, these are the two cases that we have to deal with. Case 1 is A plus C plus E plus G is 21, B plus D plus F is equal to 10. A triad BDF up to the order, don't worry about the order, just BDF, such that B plus D plus F is equal to 10 can be chosen in the following three ways. That is 1, 2, 7. 1 plus 2 plus 7 is 10. Up to the order, don't worry about 7 to 1, 2, 7, 1, all those things will come. But don't worry about that. And you worry about only one such thing. The orders we will take into account when we are counting the 7-digit numbers. So 1 to 7. What is the other one? 1, 3. Can it be possible? 1, 4, 6. It's not possible. So next is 1, 4, 5. Agreed. And the next is 2, 3, 5. These are the only three triads up to the order such that the digits of the triads, sum of the digits of the triads is 10. And again, concluding these are the only three things is also a matter that will be difficult for a student. But many students will write these three. It's okay. So these are the three things you will get it. Now, take the first case 1 to 7. Take the first triad 1 to 7. Having chosen 1 to 7, the remaining fellows. What are the remaining fellows? 3, 4, 5, 9. The sum will be automatically 21. So a quadruple ACEG up to the order such that the sum of the digits is equal to 21 can be chosen in only one way, that is 3, 4, 5, 9. Obviously, for if you leave 1 to 7, the remaining integers is 3, 4, 5, 9. So similarly, for 1, 4, 5, 2, 3, 5 can be discussed, and we apply the counting principles, and we get the number of 7-digit numbers using the counting principles, and switch to the table. Okay, we'll go to the table. So take the case 1. This is the case 1. So BDF up to the order, and the BDF up to the order which we have already seen, 1 2 7, 1 4 5, 2 3 5. And if you take 1 to 7, uh, the number of triads means the number of permutations of 1 to 7. These are three digits. Therefore, 3 factorial triads you will get. They are the permutations of 1 to 7. And for 1 to 7, ACEG up to the order such that the sum is 21 is 3, 4, 5, 9. Obviously, so leave 1 to 7, the remaining ones 3, 4, 5, 9. So corresponding to 3, 4, 5, 9, if you permute them, the number of quadruples you will get. So 4 factorial permutations of 3, 4, 5, 9 you will get. So for each triad, you will get factorial for permutations of ACEG. And for 3 factorial permutation of 3 factorial triads, you will get 3 factorial multiplied by 4 factorial 7-digit numbers using the fundamental principle of counting, that is the product rule of counting. So 3 factorial multiplied by 4 factorial, that is 144. For 145, 3 factorial permutations of 145, and if you leave 145, the remaining is 2379. The sum is 21. And how many such quadruples will be there? 4 factorial permutations will be there. And again, use the product rule. You will get 3 factorial into 4 factorial, that is equal to 144 7-digit numbers. Now, in the 235 case, you will get 3 factorial and the remaining ones are 1479. So that is the quadruple. So whose sum is the sum of the digits is 21. So use the again the counting principle. Put the product rule as above, you will get 144. So the total number of 7-digit numbers in the case 1 is, use the sum rule of counting. The sum rule of counting is first one plus second one, the third one. That means 3 into 3 factorial into 4 factorial, that is 432. So this is in the case 1. So we go to the case 2 similarly. Now we consider the OR case. So case 2, A plus C plus E plus G is 10 and B plus D plus F is 21. A triad BDF up to the order such that B plus D plus F is 21 can be chosen in the following only one way. What is that one? 5, 7, 9. And having chosen 5, 7, 9 and the remaining fellows 1, 2, 3, 4, whose sum will be 10, will be the quadruple. So suppose a triad is chosen, only one case in this case, 5, 7, 9, and a quadruple ACEG up to the order such that the sum of the digits is 10 can be chosen only in one way, that is 1, 2, 3, 4. Then use the counting principles and count the number of 7-digit numbers that you are forming and switch to the table. So case 2. So we have the triad 5, 7, 9 and the number of triads is 3 factorial and the quadruple is 1, 2, 3, 4. The number of such quadruples is 4 factorial. Use the product rule. You will get 3 factorial into 4 factorial, that is 144. 7-digit numbers will be formed. So in the case 2, the total number of 7-digit numbers is 144 only. So we summarize the case 1 and case 2 now. So in the case of case 1, the total number of 7-digit numbers in case 1 is 432. And again use the sum rule, then sum rule of counting. Then you will get the total number of 7-digit numbers is 432 plus 144, that is 576. That's your answer. So the total number of 7-digit numbers is 576. So that's your answer. Our answer is 576. And that is a very detailed discussion of the problem on counting from the section permutations and combinations. And my personal view is that in the examination, you know, and that too it's a dash even, that means you have to fill up the blank with a single answer, that is 576. is very difficult in the examination, and considering so many cases. But however, there will be some students, some intelligent students will be there. They will be definitely be doing this one. They might have done this problem, earlier in their classroom exercises. So I'm sure that you understood the solution of this problem, and I wish you all the best. Thank you.